So last time I talked about if you have a matrix equation in row echelon form, how that makes solving it quite simple. And today I'm going to talk about how you reduce to row echelon form. So let me first begin by just recalling where we were. Suppose you've got a matrix equation that's already in row echelon form. You look at the columns where there's no pivot, and of course the pivots here are circled A1, A2, and A3. The columns with no pivot correspond to the variables x3, x4, x6, x7, and x8. Those are the free variables. And the solution is going to be each of the other variables will be expressed with these left arbitrary. So for example, the first non-trivial equation you're going to get is from this row, which involves a3 times x5, and you'll conclude that x5 is equal to something involving x6, x7, and x8. And similarly, when you get up to here, you'll have x2 is something involving the higher numbered variables, all of them from x3 to x8, and so on. And before I go on, I just wanted to make one comment about this, which is it might look a little confusing why the free variables are sort of scattered. They're not just the ones at the end here, but they're these ones over here also. And a useful way to think of that is just the following observation. If you were allowed to do column operations, which amounts to changing the order of the variables, that's perfectly good thing to do. So changing the order of the variables amounts to, for example, you could interchange these two columns, and that corresponds to interchanging the variables x3 and switching the variables x3 and x5. And if you did that, you could get the matrix into this form: A1, A2, A3, and then everything else is at the end. All these zeros are out here. And I mean, you would have switched the order of the variables here, so you'd have x1, x2, x5, x4, x3, and so on. Anyway, the point is that if you had it in this form, then it's clear that the free variables are here, the ones at the end, the last 5 variables. And those are all sort of the same, and then all of the others are solved in terms of those. So that's just an explanation why it's these columns with no pivots that are the free variables. You can think of moving those to the end. Okay, so now let's go on and talk about reducing to row echelon form, and I'll do an example. Okay, so let's look at a random matrix here, which I've labeled some entries, and just talk sort of roughly how we would get this into row echelon form. Well, the idea is really it's very similar to what we've done before in the non-singular case. So the first thing you do is let's say, for example, that this first term was not equal to 0. Well, then you can use that to kill all the rest of the terms below it. You can make all of those equal to 0. Right? Because you just add the appropriate multiple of this row to all the rows below, and you can kill all of those terms. Okay, now let's say you've done that, and you're done with this column. Now you move on to the second column. In the second column, these numbers have changed because you added multiples of the first row to them, but let's not worry about that. Suppose you're here now, and you want to do the same thing in the second column. You don't care about this first term because this is a pivot, and anything to the right of the pivot you can consider you're done, and you're basically looking at this matrix here, and you're allowed to add multiples of this any row to any other row, and because you have all zeros in the first column, it won't mess that up. So let's say, for example, that let's suppose B2 was equal to 0. Well, you would have liked to have used it to kill everything below it, but you can't because it's 0. So a typical situation would be if B2 was 0 and C2 was not 0. When that's the case, what you do is you switch these two rows in order to switch this. And again, in the first column, these are all zeros, so you don't mess anything up there. And after switching these two rows, you can go back and assume that B2 is not 0, and it's C2 which is 0. And now whatever the rest of the entries are in this column, you can make them equal to 0 using B2. So you've handled the second column. And you just continue in this way. Now, how can you get a column? What different can happen? Is there anything different than what I just described? Well, the one other situation could be let's say in the next one, you're looking at this column. And let's say if B3 is not equal to 0, then you use it to kill everything below. So suppose B3 is equal to 0. Well, if C3 is not equal to 0, then you do what I just said. And similarly, C4, if any one of these is non-zero, you can switch it up to here and kill everything below. So the only case where that doesn't work is if all of these are already 0. And that certainly can happen. So now what does that mean? What that is this is a column with no pivot. When that happens, that's exactly what gives you a column with no pivot. I should go back and circle the pivots. The first one I got, the pivot was here. The second one I got, the pivot was here. And the third one, there's no pivot because everything from here on down is 0. Now, it could be there's some non-zero stuff up here, but I don't care. When you're talking about pivots, you're sort of working your way down. And so there you go. You're done with that column, and you move on to the next one. And that's the algorithm. So let's do an example. Okay, so let's do this example. Let's reduce this matrix to row echelon form. So you start here, and you have your first pivot right away, right here. And you can use that to kill these two terms. So let's do those one at a time. So you don't touch the first row. Then the second row, you add -1 times the first row to the second row. And you add -2 times the first row to the last row. To get this. So that's 2 steps. Excuse me, this last entry is a +1. I added -2 times the first row to the last row. And okay, so let's circle my pivot again. There's my pivot. So I'm done with the first column. And I go to the second column, and I look here, and that's a 0, so that's not a pivot. And below that is another 0, so that's not a pivot. So this is a case where I have all zeros and no pivot. So I'm done with this column. And remember, this 2 doesn't matter because it's to the right of this 1. And what you can do is you can start to draw your staircase. Right at the beginning, anything above that doesn't matter. And since this isn't the pivot, you go across. And you go to the next column. And what do we have over here? So, well, this 2 is a pivot. So you use that, and I'll write the result down here. You get 1, 2, 3, 1, 0, 0, 2, 1, and then you add minus this row to this row, and of course that gives you all zeros in the last row. And now you're done. This is in row echelon form. There's the steps, and here's the 2 pivots. And there are 2 free variables corresponding to x2 and x4. So let's do an example of an actual solving an equation. So suppose we had a system which we reduced to row echelon form, this one right here, and after your manipulations, the equation came out to be like this. So it's 4 variables, and the target is a vector with 3 entries. And I was saying that this is very easy to solve. And what do you see? Well, if you look at the last row, that gives the equation 0 is equal to the last entry over here, which is 0, and so far so good. And the second row gives the equation 2x3 plus x4 is equal to 2. And because you now have a free variable floating around, you can certainly solve this. You let the free variable float, and you get that x3 is equal to 1/2 2 minus x4. So again, pick any value for x4, and that will give you a unique value of x3. And notice there's no problems with zeros or anything. If x4 can be 0, you're not dividing by 0. There's no problems. Every value of x4 gives you a value of x3. And the final equation is the first row, which gives you x1 plus 2x2 plus 3x3 plus x4 is equal to 1. All right. Now, what do we have here? X4 is a free variable. So let's say that x4 is fixed at anything. Then x3 is determined. x2 is a free variable, so I'm not going to try and set that. And then I can solve this for x1. Okay, so let's see what happens when we do that. So I'll try and squeeze it in down here. What you get is that x1 is equal to 1 minus x4 minus 3x3 minus 2x2. And let me make this a 1. That's my x1. And on the right-hand side, I'm only allowed to have free variables. So I need to replace this x3. So what I get is 1 minus x4 minus 3 times 1/2 2 minus x4 minus 2x2. And that's the general solution. I seem to have run out of There we go. There's the general solution. So let's just stare at this for a minute. This says x1 is equal to an expression with two free variables on the right-hand side. There's an x2 and there's an x4. So there's a two-parameter family of solutions. You pick any value for x2 and x4, and that gives you a unique value of x1 and also x3, and that's all of the solutions. All right, let's do just a tiny variant on that one. Let's take the same matrix on the left-hand side and just change the target vector and see what happens. So what I did here is I put a non-zero entry right here, this 1, and the very first equation that you get is 0x1 plus dot 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 0x4 is equal to 1. Bzz, and you lose right away. So this has no solution. So you can talk about free variables all you want. There's nothing you can do to even get started. And that's the general pattern. If you can find any solution, you'll find an infinite family parameterized by the free variables, and otherwise there are no solutions. I'm not going to talk too much more about general systems and how many solutions they have, so we'll do some examples in class. I want to focus on a particularly important family of equations, and those are called homogeneous. So a homogeneous equation is simply one of the form a times x is equal to 0. So the homogeneous condition is that this this vector being 0 is what makes the equation homogeneous. So the 0 vector, of course, is just a bunch of zeros. And what's nice about homogeneous equations is they always have a solution. Obviously, if you take x to be 0 of the appropriate size, by the way, this is a matrix, a vector of size m, and x is a vector of size n. It might be different, but anyway, you can take the 0 vector of whatever the appropriate size is for x, and that will make this equation true. So you never have to worry about there being no solutions. But a natural question then is, what about other solutions? So this is called the trivial solution of a homogeneous equation. It always exists. And usually when you're talking about homogeneous equations, you're interested in, are there any others? Well, how many others? 1 or 10 or 1,000? We saw before that an equation either has the number of solutions of any linear equation, homogeneous or not, is always either 0, 1, or infinite. And in this setting, we've already seen that there's one solution. So if there are any more solutions, it's because there are infinitely many. And how can that happen? Well, that's if there are free variables. So suppose A is an m by n matrix, and as usual, we'll let R be the rank of A. Then the number of free variables is n minus the rank. So the condition to have more than one solution is that the rank is less than n, the number of columns. All right, so this is quite an important result, so let me state it as a theorem. Suppose you have a homogeneous equation, ax is equal to 0. And I'll write out that A is an m by n matrix. And so that says that x has n coordinates, and you're setting that equal to the 0 with m coordinates. All right, and the theorem is the following. The first part is what I just said. This has infinitely many solutions. If and only if the rank of A is less than n. And a special case of this is if m is less than n, then it has infinitely many solutions, guaranteed. And finally, if m is equal to n, then it has infinitely many solutions, is exactly when A is singular. Okay, so the first thing is what I just said. If it has infinitely many solutions, that's because there are free variables, and there are free variables exactly when the rank is less than the number of columns. This part B, why is that true? So if you have an m by n matrix, and let's picture it as being m is small and n is big, remember the rank of a row echelon matrix is the number of pivots. And the number of pivots, well, it's obviously less than or equal to n, but it's also less than or equal to m. So the number of pivots is less than or equal to m, and this is the rank. So the rank of a matrix is both less than or equal to both m and n, and since it's less than or equal to m, and m is less than n, the rank is guaranteed to be less than n. And by part A, if the rank is less than n, that says it has infinitely many solutions. And that's just the case where there are more variables than equations. Right? N is the number of variables, and m is the number of equations. And we've already talked about this last one quite a bit. This one right here, remember a square matrix is singular exactly when its rank is less than the maximum. So, and another way to think of it is that you can, if the matrix is non-singular, you can take the inverse to solve it, and therefore the only solution is 0. There's one point I want to clarify here. I think the book was a little bit vague on this, which is the notion of rank. So what exactly do I mean by the rank of a matrix? Well, if A is in row echelon form, we said that the rank is the number of pivots. Okay, but what if it's not in row echelon form? What are we talking about? The rank? Um, well, if it's not in row echelon form, what you you just put it in row echelon form. You say the rank of A is the rank of um, A sub E, where this is the row echelon form. And so it's the number of pivots. So you put it in row echelon form, count the number of pivots. Now, row echelon form is not unique. You can tinker with it. You can get different pivots. You can get different entries. But the number of pivots is always the same. So even though row echelon form isn't unique, the number of pivots is is always the same, no matter which row echelon form you take. And that's the number, since when you're solving the equation, you might as well put it in row echelon form. That's the rank which comes up in these calculations.